In this slide, we will talk about two terms which is necessary for the error propagation. One of them is condition and the other one is stability. If we define condition, it is a condition of a problem is related to its sensitivity to changes in input value. So the change of input value, how much does it affect the result of the problem? It's called the condition of the problem. Basically, it's based on the sensitivity. And the numerically unstable means if the uncertainty of the input values or the error of the input values is grossly magnified by the numerical method, this will occur. So if the numerical method changes the input values too much, it means it is numerically unstable. Let's have an example about this and see what's going on over here. In this example, we will use just first order Taylor series. And if you remember, the first order Taylor series is we want to find fx with fx plus f derivative x and the step size or the difference. So simply here we did a different explanation of the Taylor series. We wanted to find the real value using the predicted value. So this is the predicted f value or f value with the predicted x value, and the derivative of the function with the predicted x value, and the difference between the actual value and the x value. So if we want to also write down the relative error, we know that it is just, let's say, of fx. It is shown by this epsilon value. Fx is equivalent to the difference between the real value and the predicted value divided by the real value. We already know this. And we can say, based on the Taylor series, we can say this is almost equal to this approximation. So fx, and if we move this over here, fx minus fx tilde, or the predicted value, divided by the fx. In other words, we can write this way for the error. So this fx is this value, and minus this one, these are cancelling out, and this only remains actually. So let's write it down. The first term, fx, is the Taylor series at the top, fx tilde plus fx tilde x minus x tilde, and the second term is just fx tilde. So for this one, I wrote this here, and this is the same as this, and this is divided by, again, the fx value. And for the denominator, we want to have just, we assume that this can be predicted by the predicted value. So for that, we will write this fx only. And you can see that these will cancel out, and only remaining term is the derivative times the difference divided by the prediction. And for the relative error of x only, then we can say epsilon x is equivalent to x minus x tilde divided by, again, we are writing x tilde instead of x to have a prediction. And we will have a ratio of these two, ratio of these, and this will defines a condition number. Which gives us just x tilde fx derivative value and fx. Simply we divided this by this one, and you can see the x minus x tilde values are cancelling out, and the remaining is x, and it goes up here, and here remaining is the derivative, and at the bottom only the fx value remains. So we have this value as the condition number, and you can see that the derivative divided by the actual function value with the predicted x values and the prediction of x gives us a condition number. And there are some conditions based on this. Let's write them down. If condition number is equivalent 1, then epsilon fx is equivalent to epsilon x, which means actually the denominator and this one is equal. That's why this becomes 1. So that gives us this value. These are equal to each other because these are divided already. So this is simply, we can say this is actually equivalent to efx divided by ex, and if these are equal to each other, that means the result is 1, means identical. These are identical. So the error in the function value and the x value is identical, the same. Otherwise, let's write with the black color. If condition number is greater than 1, then that means the relative error is magnified. Which magnifies the uncertainties in computation of x actually. So we can write it here. Magnifies uncertainties or errors in computation of x. Computation of fx, the function. Which means we can have very large values. So the magnification is too large. That means we have actually ill-conditioned results. This means ill-conditioned. We don't want this because it actually increases the uncertainties too much in the prediction, and it doesn't give us a correct result. So and we can understand this easily by simply making this division beforehand. So lastly, if the condition number is smaller than 1, then the relative error is decreased. And this is good actually. The error is decreasing, so this is what we want, and this is a positive condition, let's say. In this slide we have an example to practice the condition number, and it says we want to calculate or interpret the condition number for this tan x function, and for the x the prediction is this, and for again we have another prediction here, and the exact values of these we can write. This value is actually 0.7279. You can calculate them, and this is 1.5865. Okay, we want to have the condition number now. You know that the condition number is just the derivation of efx, epsilon fx divided by epsilon x. So epsilon fx was, if you remember, this was obtained as x tilde times the function, which is here the tan x function. We can write it down as, sorry, the derivative of the tan x. So the derivative of this is 1 divided by cos square x. So we can write here 1 divided by cos square x. And at the bottom, we only have the fx, which is tan x. And these are tilde because we will use the predictions. Simply, we will evaluate this. And so the first x value is this value, and the second one is this value. Let's use the first one. For x tilde is equivalent to 0.7279. The condition number is equivalent to, so x tilde is 0.7279 times 1 divided by cos square 0.7279 divided by and we need to make a correction here. This is 1.7279. So these are all. Let's erase them and write 1.7279. And the denominator is tan x, which is tangent 1.7279. And if we calculate this, you can make the calculations. It's minus 11.2. And the other x value, x tilde, is 1.5865. Then the condition number is 1.5865 times the derivative cosine square 1.5865, and these 1865 and 17279 are in radians, so be careful on calculating them using your calculators. This is divided by the tangent 1.7279, sorry, 5, it should be 5865. Then the result is minus 101. You can see there is a crazy increase when we change the x value from 1.72 to 1.58. So the condition number is crazy small with negative value, much worse, which means this is worse and this is not. So having a value of 1 is ideal, but if we getting away from it, it is not good. And actually this one means the function is ill-conditioned. Here the situation is much worse. Much worse, ill-conditioned, let's say. And the main reason of it is the derivative, because this derivative value over here, this one, is too big, 40.86, but here it is much bigger. This is 4053. So it's much bigger, and having an increased derivative value increase this too much. And so we can say the derivative 1 divided by cos square x is the main reason of having an ill-conditioned problem or approximation, let's say. And this makes sense because near pi divided by 2, near 90 degrees, the tangent approaches both positive and negative infinity. So this pi divided by 2, and adding very small makes this more to infinity, and it increases this and increases this value. So we need to be away from the 90-degree value or p divided by 2 value as much as possible. So here we added slight deviation. Sorry, here very slight deviation. There is a little bit more deviation, more getting away from p divided by 2. That's why we have a better result. So if we get further away from p divided by 2 value, then we will have better condition numbers, then we can have better predictions. We can say this happens because tangent approaches infinity near, and positive or negative doesn't matter, infinity near pi over 2. And if we get away from pi over 2, then we will be able to get good results according to this solution.